So far, most of the rates of change question we've been looking at involves differentiating to find rates. But of course, there could be questions where we go back the other way and we have to integrate. So let's look at rates of change and integration. Integration, of course, allows us to go backwards so we can find the original quantity from the rate of change. If we know the rate of change, we can go back to the original quantity itself. So here's a 2017 question. Water flows into a tank. It's given by dV to T is this lovely expression. V's volume in litres, T's time in seconds. And initially the tank's empty. Find exactly the amount of water in the tank after 10 seconds. So right, we know dV to T is 2T on 1 plus T squared. This is what I was talking about the other day. Do these things as definite integrals rather than indefinite integrals, and then you don't have problems trying to work out with a constant, and it just automatically solves itself in the problem itself. To do that, we separate the variables, which, yes, I know we haven't looked at differential equations yet, but we will see it in more detail. But it's exactly what it says. We simply separate the variables so that all the variables on one side are the same. Now, technically, on the left-hand side of this, the variables aren't the same because I've got V and T together in dV to T. So we separate them. And then I integrate both sides. Now, the limits. They've told me when T equals 0, volume is 0, so I match that up. We want to find volume when time is 10. So we now just have to solve this equation. Now, when you've got an integral like this on the left-hand side, when it's just dV from 0 to V, then it's okay. You know, well, that's got to be V. Because if you think about it, integrate dV, you get V. Sub in V, you get V. Minus sub in 0, or minus 0 is nothing. So usually that sort of one on the left, we just jump straight to V. Although I just totally contradicted myself, haven't I? Oh well, of course you don't have to. Alright, on the right hand side we have a log function. We've got derivative over function. Oh, there it is now, V. And we get log of 101 over 1. Remember, when you're subbing into logs, you know you're going to get minus the log, so you can put that all into one log function straight away, because it'll be the top minus the bottom. And we get log 101. So we know there is log of 101, whatever that is, litres of water left in the tank. Acceleration of a particle, there it is, 4 cos 2t. Standard stuff, x is displacement in metres, t is time in seconds. Initially, we're travelling with a velocity of 1 metre per second. When does the particle first come to rest? Okay, well, I'm going to write acceleration as dV to t. Then I can separate the variables out. They've told me when t equals 0, v is 1. We want to find when v is 0. Okay, we solve this one. This time with the left-hand one, I will integrate it because it's not going from 0 to v. Okay, so we're going from 1 to 0 on the left-hand side, right-hand side, 0 to t. So we get negative 1 is equal to 2 sine 2t. Sine 2t is negative a half. Notice I haven't worried about the quadrants in this one because they've said the first time it comes to rest. So I haven't found all the answers. I know I just want the first one. So when's the first time sine 2t is negative a half? Well, that's in the third quadrant. So 7 pi on 6 would be the first time. Divide by 2 and we get t is 7 pi on 12 seconds. This one here was a little bit more involved. Raindrop. Conveniently, it's a sphere. Thank goodness for that. We've got a formula for a sphere. Evaporates at a rate depending on its surface area. Ooh, we've got a formula for that too. The rate of change of volume is given by this, minus 10 to the power of negative 4 times A. And A is the surface area of the raindrop. Show that dr to t is a constant. Hey, I want to work out what dr to t is. How the heck am I going to do this? Well, we know dv to t. If I've got something that links volume and radius together, which we do, of course. So dr to t would be dv to t times dr to v. Volume is 4/3 pi r cubed. It's the one I always love. When you differentiate the volume of a sphere, you get the surface area of a sphere, 4 pi r squared. So in fact, dv dr is the surface area of the sphere. So it's equal to A. Now, let's now sub that in. dr to t, they told us was minus 10 to the power of negative 4. A, we want the reciprocal of dv dr, so times 1 over A. The A's cancel. I'm left with a constant number. So, yep, it decreases at that constant rate of 10 to the power of negative 4. How long does it take for a raindrop of volume 10 to the power of negative 6 meters cubed to completely evaporate? The R to T is minus 10 to the negative 4. Volume, because of course I don't know the radius of this raindrop yet. So I've got to work that out. And it turns into a wonderful number. I did not bother going to my calculator. I've just left it as the exact value. The radius turns out to be the cube root of 3 times 10 to the negative 7 over 4 pi. Whatever number that is, I've probably got stored in my calculator, but I'm not going to bother writing it down. Separate the variables. Made the integral interesting to write. The bottom value is the cube root of 3 times 10 to the negative 6 over 4 pi. It's going from that to 0 because we want it to evaporate. And, well, on the right-hand side, oh, did I do it this time? I've got the t going from 0 to t, so we can just say t. Yes, I did it that time. Okay, so t is 10 to the power of 4. R is going from 0 to the cube root. Notice the negative, I've swapped the limits around there to get rid of the negative. So we end up with 10 to the power of 4 times the cube root of 3 times 10 to the negative 6 over 4 pi. Now I'll go to my calculator and I got 62 seconds as the answer. 9F.